This is our second video on implicit differentiation, and we're going to look at cases where we're applying implicit differentiation. And you can see I've written in an equation which we have to find the gradient of the tangent to the curve at 0.13. So because from our previous knowledge of calculus, we know that when we've got the derivative dy dx, we've actually got a gradient function. And it tells us the story of the gradient at any point. And also we know the nature of tangents at a point. So the gradient of a tangent at a particular point is also the gradient of the function at the particular point, and that's important in this video. So whether we're finding the gradient of the function at a point or the gradient of the tangent at a point, we need to follow the process of differentiation. And in this case here, where we have functions of both x and y, we're going to go with implicit differentiation as per the previous video. So there's the start of the process there, and we move through and we've got 4x. Now with ones like 2xy, you can use the chain rule explicitly there, or if you've actually been a bit more automated, I guess, you'd be able to go straight to the answer. And in that middle term, there's also a product rule apparent too. So we have the last two terms, there's chain rule and a product rule apparent according to implicit differentiation. Now I've tried to use some colors there. So the light green zones from the first line to the second line transfer. So we have, that is, by the way, a dot, and that's multiplication right there. Okay, so we have inside the light green, d dx of 2x times y plus 2x times dy dx using the product rule. And then the yellow bit here, we have 2y dy dx in the yellow zone there. That equals 0. Okay, now we fix all that up like so there, and notice the grouping the middle term together all in square brackets because all of it's being subtracted from 4x. And so we have 4x take away 2y take away 2x dy dx plus 2y dy dx equals 0. Now doing some rearranging, because we want to get dy dx isolated, and I've just done some algebraic rearranging there. And we want to get dy dx as a factor, and we have that as a factor. So we have on the left side dy dx common to 2y less 2x. And then we can isolate dy dx as 2y take 4x over 2y take 2x. Then we can divide through on the right hand side by a factor of 2, y take 2x over y take x. We can't have where y doesn't equal x, okay, because we get 0 in the denominator there. So that's our gradient function, and dy dx is a gradient function. It will give you the gradient at any particular point, and it'll give you, it's basically the gradient of the curve, the story of the gradient of the curve. Now at 0.13, both the curve and the tangent have this gradient we're about to find. So at the 0.13, subbing in x equals 1 and subbing in y equals 3. So in the gradient function, or dy dx in other words, we have 3 minus 2 over 3 minus 1, which is a half. So the gradient of the tangent at the 0.13, or indeed the gradient of the curve at the 0.13, is a half.